Hi, today the main topic is the bit tree, the part 4. This is actually the last part of explanation of bit tree. Last video I just talked about why is the delete operation in the bit tree, and why the reading from the disk is slower than the memory. And also I talk about how to do the example, how do we handle when there's unbalance in the bit tree. And now in this video, I'm gonna recap the last video, and I'm also gonna trying to talk about some kind of like practical way, my experience of implementing B3 from the scratch using my own language, which is TypeScript, the type language of the JavaScript. So let's begin. Let's do it really fast and simple. First, let's recap the insertion first. So insert, let's say the minimum degree, let's say 2. So our max keys is 2t times 2 times t minus 1. So it is gonna be 3, and the min key is gonna be t minus 1. So which means that 2 minus 1 is actually the 1, and also the primary key index. So primary key is that the key that gonna be parent when there is the already full node. It's actually t. It's also t minus 1. It's actually 1. Not this one. So let's begin of it. So insert some part. You insert when you try to insert, let's say, let's just put this part on it. For two, you should really do the sorting because you have to find the primary key of it. 2, 3, 4, 3. And when you try to put 6 here, it's already full, right? I think the node is very big. I think this is gonna be really nice. Yeah, this is much better. 2, 3, 4. And when you insert 6, it's gonna be full. So you have to make the primary key into parent. So our primary key index is 1, which is 0, 1, which is 3. So you make 3 as a parent. So there's gonna be pointy here. Now you insert next part. 8, 11, 120. 8, 11. So this node is already full, right? So you have to make also the primary key as a parent. If you put 6 here, and you should merge it like this. 3, 6. So gonna be, let's put middle here. Let's make it like clean and red with the red drawing. 6, 3, 6. And this is the pointer here. So this is the pointer here. Nice. So when trying to insert 120, let's just erase this part. And now, let's insert till 113. So 113 is here, and when trying to insert 120, so the 113 is gonna also primary key. So let's put like this part. Now let's insert 105. Since we can just insert 105, 105 is smaller than 113 and bigger than the 6, so you have to go to this part, which is, let's insert in here, 105 and 104. If you're trying to insert 104 in here, 104 here, this 104 is gonna be also primary key. So 3, 6 and 104. And so this parent So this parent is already 4, right? We have to make this 1 to 4 into parents. So 1 to 4, let me go here. So actually this drawing is so ugly, so let me just try to redraw this stuff. 3, 6, 3, 6, 2, 4, 2, 4. Two, 4, and we have to put 8 probe on here. 11, yeah. So put here like this, and 1 to 13. Yes, 1 to 13. This part, so you go here with the 1 to 5, and you put 1 to 20 in here. 1 to 4 here. Yeah, it's more better than before. Like this, yeah. It's actually 1 to 4. So this is like just the point here. So this is really nice. So this is really how insertion is gonna be. So the thing is that the insertion is really easy. You just have to find which is the primary key, and when it's full, you split in and you put the primary key as a parent. If your parent is doing is also full, you do the same stuff what you did on the children. But I talked about the deletion on the last video. I think this one is really hard. The minimum keys is 1. Our max keys is 3. I think the core thing is 1, the minimum keys. You have to make sure that the node is not less than 1. And let's say we wanna delete 8. Deleting 8 is really easy. You just have to find here. 8 is smaller than 1 to 4. Go here. 8 is bigger than the 6, and you find like here. It's really easy, right? And now, if you try to delete 8, it doesn't break the rule of the min keys, the length of the min keys. So you can just delete 8. You already delete 8 here, right? But next part is gonna be really tricky. Let's say you wanna delete 4. So the deletion is basically if you delete, does it cause underflows? Is really important in the B tree. If it's not, it's gonna be really easy. Example, if you delete 8 in the leaf part, leaf meaning is that there's no children, there's a loss of it. So these are the leaf. So if you delete, does it cause underflow? If it's not, you can just delete it. But leaf is, so there's a two-way of it. Leaf, so delete key but inside leaf, but delete key if it's in the internal node. So internal node is that the one that exit leaf. These are the internal node and these are the internal node here, but except this part, internal. So there's a two delete operations. If it's a leaf and internal. Leaf node, you can just delete it. Internal node is that if you try to delete it, regardless of what we're gonna be underflows, you just have to borrow from the children. So that's gonna be tricky part. But let's skip the internal node first. Let's skip this part. Let's say you wanna delete the 4, which is in the leaf key, right? We're trying to delete 4. is really underflows. So you have to do one thing, not one thing. You have to think about more. You have to borrow from siblings. You have to borrow from siblings. So which means that you have to check those kind of pointer. Sorry, you have to check the children of here. Example, you cannot borrow from the 2 because if you're trying to borrow from the 2, it's gonna be underflows. If you can borrow from the here 8. So you can delete it, you can put it like this part. That's kind of easy, right? But let's talk about really practical way. We are software engineers, so we have to really implement. We can implement it. So your current node is in this part. So let's say let's say your node let's say you find, so there's like find function here, find key, and there's a target key. Let's say the target, we just talk about target keys 4. So you somehow answer that target key. So let's say const founded. This variable name is really bad, but founded. So if you founded and you inside founded, let's say you put some kind of multiple metadata in the founded variable. Example, founded the index means that the index of the key that founded, which is the 0 here. So and your current node. So let's say this node, your current node, that keys. So because these are the keys, right? Keys that they founded that index. So it's gonna be 4. But the thing is that you really have to think about borrowing from the siblings. But if you're like in this part, it's really hiding from here. So you don't know, you have to really track all of the siblings. But if you're on the left node, like if you're pointing the 4, you don't know what to borrow. So my approach was doing sending the parent here, parent node. So example, if I'm trying to explain the code, so there's a function deletion. Function deletion, so there's gonna be page here, current node, and parent node. So my approach was using parent node past this part and pass current node into this part. So if the key is here, okay, but if you're trying to delete this key, you have to check if node keys is under than the main keys. So you have to, if it does, you have to check about this parent pointer and check the siblings of it. So that's gonna be really also tricky part. Example, these siblings is okay because the index of this is 0, 1, 2. Based on that, you can just plus 1 plus 1 equals to the sibling index, and 1 minus 1 is your also the left sibling index. But what if you have also like this part? Let's say you want to do 105 as an index here. So you also have to check about the left sibling that is no value. So that's gonna be really tricky part. So let's just, so whatever. So now we able to borrow from the right. So we can just delete this 8, borrow it, and we can just put here, right? But the tricky part is that when I'm trying to insert on the 8, it's already breaking the binary tree, the bit tree, because bit tree is extension of the binary tree. Because 8 is actually bigger than the 6, but you don't. If you're trying to put here, you can really, it's really breaking the bit tree stuff. So what you have to do is, you have to put 8 on the 6 and send 6 on the child. I think this is really kind of easy, but there's a more difficult thing is this. Let's say you wanna delete 105. Let's say just 105 is quite nice. Let's just say we don't have 6 here. Let's say we just want to borrow the 4 here. Delete the 4 here. Since you cannot borrow from the siblings, the other approach is borrow or pull the parent and merge sibling. So you borrow from, so what you have to borrow is, let's say 3. You can just borrow 8, but rather you put 3 in here, but you now merge with the left part. Which is gonna be 2, 3, 4. Since this doesn't break the bit tree on the this node is an underflows, and this parent node is underflows, is really good. So you can just delete now. Your target key was the 4, right? So you can just delete 4 now. So it doesn't break any rule of it, so it's pretty fine. But what if your target key is 121? You do the same stuff. You borrow from the 13 and you merge it. But if you're trying to delete 13, there's nothing here. So that's kind of a tricky part. Your current pointer is here, and let's say you just can't get the parent pointer via the function arguments. But if it is underflows, there's no key of it, you have to do the same stuff what we just did. You have to look for the parent. If it's underflow, you can just borrow from the siblings, but if you cannot borrow from the siblings, you merge with the one parent. So you go merge here, you put 104 here, and you merge with the 8. So this is gonna be 104. So 104 is gonna be here. So it's gonna be like this. So this is how you really rebalance the bit tree. But I'm just saying, but those kind of things is really hard, because since the 104 is parent pointer, you can't really do the recursion stuff because in the root there's no parent node, even though you can. So if you're trying to call the recursion function using parent, you have to also send the argument of the parents. So this is gonna be tricky. So I think my best recommendation is if you're trying to implement the bit tree on deletion, you don't use recursion. You have to use wire syntax, because if you're trying to use recursion, there's a bunch of pointers, you cannot even track it. So it's really hard to manage. So I think this is it. So essentially, just recap and how do you really make it? Let's say using some kind of like my code here. So this is it. Actually, this is my journey of my software engineering. And I don't know you guys looking at this video or not, but I'm pretty sure you guys almost not bad, because there's only like 10 or it might be 50, but I know I'm shy of like drawing stuff, because I'm a very introvert person, and this is even not my native language. But the reason why I'm using this language and trying to explain those kind of things. And I know it is hard, but I believe that if I'm pushing myself every day explaining some kind of difficult theory, someday I'll be better. So that is why I'm doing every day, because I want to be better, because I really like my area. I'm software engineer and front end development, web engineer. So I think this is my reason for it, because I have passion on it. I really like it, and I believe that the most important thing is that also the coding and engineering, but also communication. I'm trying my best to enhance my communication as much best. So I think this is it. I have a nice day, next time. Bye bye.